Sam, can you hear me? I may have just figured out a much better way to get slides to people if they're on Teams, which is kind of late, but late is better than never. So what I want to start with today is this graph. And this particular graph in the dark blue line right here is something that I will want you to draw on your next exam. So basically all of my exams, there is a graph that you have to draw. And for the next one, it's this. Because this is explaining why the acquired immune system is so important and how it acts.
Just the blue line?
Yeah, just the dark blue line, because what this is showing is your total antibody. So it's a graph of antibodies. And you can look at the total amount, which is the dark blue line, or you can individually look at IgM, which remember that's the one that's 5, I didn't do a very good job of drawing that. IgM is the one where you have 5 antibodies in one. Remember that? Mm-hmm. That's that is IgM, and then IgG is the other major blood plasma antibody. So when you mathematically add the red and the light blue together, that's the dark blue. So when you draw it, you just need to focus on the dark blue line. So what this is showing is how long does it take to make a decent level of antibodies that would help protect you in those 5 ways of opsonizing, neutralizing, agglutinating, and so on. And so this whole process is going to start when your first ever exposure to that specific antigen shape. Like the first time in your life you ever encountered that antigen shape. And from that point, we would have, from here to here, there is innate immunity going on. So during this time when you're not making any antibodies yet, your innate immunity is kicking in with the barriers and the chemicals and the processes in this time period. But from here to here is that's the time it takes for B cells and T cells to get their act together, and for the B cells to make plasma cells that start releasing antibodies. I'm using AB for antibodies. So there's a lag, what we call the latent period, from here to here, that's about 2 to 3 weeks. For B cells and T cells to do all the things that they have to do together to get to the point of having plasma cells start making antibodies. And those plasma cells are going to first make IgMs, and then they'll start making IgGs, but together the useful amount of antibody is in this dark blue line. And so this is how long it takes for acquired immunity to kick in. And when we get to about this level, that level of antibody, we can consider that to be the protective level, or the effective level of antibodies. So if you make it about, 3 weeks or so, then your acquired immune system kicks in, and at that point, you're going to be much more protected from whatever disease is accompanying this antigen. So that's the first time around. And then notice in the middle here, they're calling it variable time interval. Variable time interval. That could be months later or years later. Could be even decades later. Decades later. And the second time that you see that same shape, you'll have a really quick boost of antibodies. It doesn't take 2 weeks from the second time, it only takes about 4 days or something. And that's because here is where your memory cells start to work. That's where the memory cells start to work. So we learned last time that both T cells and B cells can make memory cells that live long and kind of wait for the next time. And when the memory cells detect their same antigen, they will produce plasma cells, which then will produce antibodies, except it's just a lot faster. This is talking about the B memory cells. And then they also, this is so cool, they produce newer and better versions of memory cells for the next time around. So every time in the future that you encounter that same dangerous antigen shape, your memory cells kick in and produce plasma cells and produce antibodies quick. And you get a really fast antibody burst, and you reach the level of protection in like 3 or 4 days, and you usually don't even get sick. That's what immune, sorry about that. That's what immune memory gives you, is the quick response next time so that you don't get as sick because you make antibodies quickly. Notice here that you build up antibodies and they go up, 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 and then they decrease. Because you basically have fought off the disease and you don't need those antibodies so much right now. They decrease. If you've seen news reports saying things like, COVID antibodies do not last long, and then they've got an exclamation point like, this is so bad and this is so dangerous, that's to be expected. And I feel like those news articles are misleading people to be more scared than they should be, because it's normal after you have a disease, you need the antibodies to fight it, but they will eventually go away because you don't need them now. So if you were to go and check someone's blood that had SARS-CoV-2, and they had it back in the summer, way long ago, they're not going to have high levels of antibodies, but that doesn't mean that they can't protect in the future because they've got memory cells. So anyway, that's my soapbox thing to tell you today. Yes, immunity declines after COVID infection, but that doesn't mean that we don't have memory cells. The other important thing about this graph is to know that the first time around, that's primary response. That's the first time you saw the antigen. It's slower, and we get less antibodies the first time around. But the secondary response is quicker and stronger, because we've got these memory cells already set to go. And then later on, notice also, these antibodies are lasting longer too. And then if there was a third time, a fourth time, a fifth time, same thing, except it just gets faster and stronger every time. Our immune system kind of keeps learning and optimizing. So this is one of the three biggest important concepts in this whole class, this graph. And so on the next exam, which I think is next week, I will want you to draw, is it next week or is it the next week? It's next week. Draw this. This is, remember, the concentration or the titer of antibodies. This is time. And what you need is the dark blue line, first exposure, second exposure. And you have to make sure that the first bump of antibodies is slower and smaller than the second one. See how this is faster and taller.
Okay, then that'd be a good graph.
That would be a good graph. But if you drew like this.
So then you just need the antibody titer, the primary response, secondary response, and then the lines, and then the latent period and the variable time interval, like those like 5 things.
We could draw it together right now.
Okay.
So antibody titer, pattern, time.
Do you just need time, or do you need the specific latent period and variable time?
I don't so much care about the variable time, but you have to have it drawn in there. But so you need to start it like you have no antibodies. And then you have the small bump decreasing, and then variable time. And then the second exposure, you get a really high bump. First exposure.
What do we need to list the first and second exposure?
Yeah. Subsequent exposure. And then say that this is the primary response. This is, it's so ugly, but this is the secondary response. And it's a big deal that this is steeper than this, and it's also taller. Steeper and taller. I think I'm gonna leave that up there. Let me slightly change this. Make it a little bit less steep. So this is the way our acquired immune system works. It's slow, but it ends up being strong, and we have cells as a part of it, and that will generally give us some lifelong protection against that particular shape that we experienced in the first place. There's two ways to accomplish this. You can kind of let people naturally get exposed to antigen, or you can give them antigen on purpose as a vaccination. So that's why I have this slide at the beginning of vaccination and at the end of acquired immunity, because all acquired immunity works this way. But you can start this either, make this part red, you can get the disease or you can get a vaccine to be exposed to that shape. But either way, that would be the first exposure. So what we would like is for most people's first exposure to SARS-CoV-2 to be through a vaccine and not from the environment. That's the hope. So getting acquired immunity can happen naturally or it can happen artificially. So there's really four specific ways to get acquired immunity. You can have natural immunity versus artificial immunity. And within both of those styles, there is an active way and a passive way. So I'm going to talk through these 4 styles, and Chelsea and Liv, these are exactly the same stuff as AMP2 and It's just different pictures of people, but everything else is the same. And constant and root, this is the same stuff we learned in AMP2. So if we say that something gives natural immunity, that means that it needs no medical intervention. It doesn't need medical intervention, and it could have happened a 1,000 years ago, before we even had modern medicine. That would be considered a natural way of getting immunity. So you can catch the disease, and you build your own antibodies. By B cell and T cell activation. That's natural. That could happen 1,000 years ago, and still today, that could happen. The other way that natural immunity is possible is mother to child. Mother to child through breastfeeding. Oh, yeah.
Is the active one.
Yeah, this is the active one, because both of these are natural. That's the active method. This is the passive method. And it's active because you're building your own antibodies. Your body is making the antibodies. The passive way is that there are mother-to-child antibodies via milk. It says via milk or through the placenta. The baby can get some of the mom's antibodies through breast milk, or there's a few that can go through the placenta, mother to child. The baby did not make its own antibodies, and because of that, the baby does not have memory. It doesn't have immune memory. So that style depends on constantly getting new antibodies from the mom across the placenta or through breast milk. That's the passive style. That's passive. But either of these ways, that could have happened 1,000 years ago, or that could happen in the middle of nowhere now without medical care, so to speak. That's natural acquired immunity. The opposite of natural is artificial. Artificial acquired immunity. And this depends on medical care. Like you would have to go to a clinic or a hospital or a doctor's office to get these to happen, the artificial acquired immunity. Artificial also has active and passive methods. So the active artificial immunity pretty much is vaccination. That's what vaccination is. So we're giving antigen in a safer way than just letting people get the disease. And then the people make their own antibodies. They're making their own antibodies after they get an injection of the antigen from the particular disease. That would be active artificial immunity. There's also a way that you can artificially give people acquired immunity in a passive way, which is the person receives IV, like intravenous through your IV person receives IV antibodies that were purified from somebody else. And some of that's happening right now with COVID disease management is if people have survived and the survivors have antibodies still in their blood, they can go and donate blood. You can purify the antibodies out of their plasma, and then you can give them to somebody else who's struggling with disease. It's not just for COVID disease that this happens, but that's an example. And if you've heard lately of the concept of convalescent plasma, that's what this is. Or convalescent plasma is artificial passive immunity. The passive immunity, remember, does not last long. Passive immunity will only last as long as antibodies last. It doesn't have memory. That's what I wanted to write about those. While I was thinking there's something else I need to say about this.
Could you say that one more time?
Yeah, I'm going to write it down actually. Oh, here's the place where I could write it down. Okay, so active immunity, the person who has it makes their own antibodies. They're making their own antibodies, and that's what makes it active. And their own immune memory. They're making memory cells as well. They're actively making memory cells, they're actively making antibodies. And so active immunity gives long-lasting protection. As long as the antigen doesn't change shape. So like with flu virus, the flu virus is always changing shape. And if you catch the flu or you get the vaccine, you make memory cells against that shape. But the next year, if it's a different shape, you have to start over, which is irritating. Coronavirus is not changing shape very much, it seems. So we think that when vaccines are developed, you'll just have to get 1 or 2 shots and not every year. But if you need them every year, people will make them every year. But right now it looks like 1 or 2, and then it probably should be long term. So if for the passive methods, whether they're natural or artificial, the person is just receiving, the person receives antibodies from somebody else. And in this case, the protection only lasts as long as the antibodies last. Antibodies don't last more than like 3 months, I think, is the longest. So this version, there are no memory cells. We're not giving memory cells to the person, we're only giving them antibodies. And whoever is getting passive methods, you're going to need constant, or let's say frequent, not constant. You're going to need a frequent supply of the antibodies from the donor or the mom. You gotta keep giving them more antibodies so that they still have it before the antibodies break down. So there's some people that they have an immune disease and they constantly need donor plasma to keep them healthy. For COVID patients, they wouldn't need it constantly, just for a while until they recover. For the baby, as long as the baby is breastfeeding, they're getting some antibodies. And currently, that and the gut flora thing are the main differences between breastfeeding and formula. We don't know yet how to get antibodies into formula for the babies. Those are the 4 styles of acquired immunity. So the rest of the time, I want to focus on just artificial active, which is vaccination. And this is an old school picture from the early days that vaccines were ever developed, and it's a propaganda against smallpox vaccination. So here's a lady getting an early vaccine against smallpox. And this cartoon is trying to show that getting that is going to make you have cow, C-O-W, cow characteristics. Because the early vaccine for smallpox, which is deadly, is to give you cowpox, which is a related shape, a related spike shape that gives cross protection against smallpox. So this was back in the 1700s, early 1800s. And from the beginning of when vaccines were ever invented, it's always been kind of controversial. Like, it's going to make you turn into a cow. It's going to put something foreign in your body. There can be side effects. So what we want to happen with vaccines is we want to give antigen. We want to give the antigen shape to allow artificial active immunity, or let's just say active immunity and we also really, really want immunological memory during this process. So we want to do that in a way that does not have the risk of the disease. That doesn't have the risk of the disease. The vaccine needs to be less risky than the disease. So back in smallpox days, smallpox would kill 30% of the people that got it, which is just staggering. It would kill at least 30% of the people. Cowpox might kill, the old school cowpox vaccination might kill 0.3% of the people. Like 100 times safer than getting the disease. These days, it's a much bigger difference between like how deadly is the disease versus how dangerous is the vaccine. What's the coronavirus death percent ballpark?
Like 1.5 or 2.
1.5 or 2. It's probably some lower than that because there's lots of people that have infections that we can't count. 1.5 or 2. We would want the vaccine to have serious complication rates of like less than 1 in a million. So that's what's happening right now with the vaccine testing. Did I tell you Han is a vaccine tester? Mm-hmm. We're pretty sure he had the placebo. But we're pretty sure our pastor had the real vaccine because he felt kind of lousy for a few days after. And they're doing the same company's test, the Pfizer vaccine. So that's what the goal is. If it works perfectly, this is how a good vaccine would work. It would be totally effective at prevention, it would be easy to store, distribute, and administer. It should be easy to store the vaccine. It should be easy to get it to the places where people need it. And it should be easy to give to people, like through a shot, or there used to be some older vaccines that they would put it on a sugar cube. And then like your grandparents and your great-grandparents would eat a sugar cube that had polio vaccine in it. They were probably much more happy to do that than kids getting shots. So if you're a nurse and you give kids shots, sometimes you'll like get kicked. Joseph kicked nurses when he was 4. And I was trying to hold him down and I couldn't. He's pretty strong. And I wasn't expecting the crazy fear and kick the nurse. 2 of them actually. I'll come back to this point in a minute. It should be cheap. It should have no side effects. And it should have lasting immune memory. Cheap, no side effects, and lasting immune memory. There are other things that we want for vaccines as well, but these are the main ones.
What would you count as like a side effect? Because like if you get a flu like vaccine, you can get sick like a couple of days after. It's not technically a side effect of it.
That technically would be a side effect. So the usual vaccine side effects are your arm is going to hurt if you got it in your arm.
Yeah.
You might feel tired. You might run a slight fever. You might get headaches. Those are the usual set. There are some more serious side effects that happen once in a while. So if you follow the news about vaccines for COVID and you read that, what was it? The Oxford vaccine had to shut down because somebody had a neurological episode. They have to stop the vaccine testing and figure out, did the person have that because they got the vaccine, or did they have that because of an unrelated reason? And so they had to stop and determine, is it because of the vaccine? I don't think it was. There was another one of the other COVID vaccines in development, I think someone died. They happened to die while they were under the vaccine test, and you have to figure out, did they die from the vaccine, or was it something else? So usually you have, like 10, 15 years for all this stuff. The rush right now is like, we got to hurry. We got to do the best we can with safety. But I'll talk some more about the side effects in a minute. No vaccine has all of these. There is no perfect vaccine. Obviously, flu vaccines aren't totally effective at prevention, and they don't give lasting immune memory, but they're still worth it overall. How much are SARS-CoV-2 vaccines going to cost when we get them? What'd you say?
200.
200? They're supposed to be free to people.
Supposed to.
They're supposed to be free to people, but somebody does have to pay for them. Who's going to pay for them?
That'd be like the government or state.
The government. Yeah. The government is already largely funding the vaccines, and they're supposed to be free for people when they make it. But no vaccine is ever totally free, and not all vaccines, no vaccine is free to make. They're all expensive to make, but what it costs to the person is different depending on what vaccine we're talking about. So COVID vaccines are supposed to be free. we're gonna be giving probably people SARS-CoV-2 vaccines without really knowing long-term memory, because we're not gonna wait 9 years to see, oh, does it last 9 years? Try to give people, and then if you have to get another one later, you might have to get another one later. The vaccine that Han and our pastor got has to be stored at -70 Celsius. That's a problem. Like, that's really a hassle if you're going to try to give people a vaccine that has to be frozen that cold until right before you give it. So when they happen, you won't be able to go to CVS and get one, I don't think. Probably have to go to Sullivan County Health Department, and maybe they'll schedule it, says like your day is June 26th.
Does it feel cold when you get it?
It won't feel cold when you get it. No. It's just that as soon as it warms up, it starts kind of degrading. So you can't let it warm up until right before you give it to the people. Yeah. And they're going to be in an injection, not like nose mist or eat the vaccine or whatever. Sam, are you able to see the writing on the slides? I'm so curious about that.
Yes, I can see the writing.
Hey. So what this means is if I can get in a room with a smartboard and do this exact thing, that's going to be the best.
What'd you do to switch it up?
Hmm?
What'd you do to switch it? You know, like make it more visible.
Screen share. So I'm screen sharing and writing on the slides, and that's going through the computer. So they're not looking, Sam right now is not looking through the OWL, which is okay, but that means that this will work in a room with a smartboard, which we're going to have for AMP2 in the spring.
Nice.
Sorry. To everybody that had to watch a bad version in the past, I'm sorry. And all the rooms are different, and this is the only room that would work with this that I've got this semester. So when we make a vaccine, we want it to give the person the antigen shape without making them sick. And there's some different ways that you could do that. These slides are kind of telling you a lot of info about vaccine categories. So I'm going to kind of circle each category and talk about what that specific vaccine is like. So there's a category called killed cell or inactivated virus. And in this picture, they're using this rod-shaped bacteria as the killed cell, and they're using this here as the inactivated virus. So in this, what you do is you take the whole pathogen, the whole thing, and you kill it if it's a cell, or inactivate it if it's a virus, because you can't really kill a virus that's not alive. So you use heat or chemicals and take the whole thing and just make it not dangerous anymore. So it's dead or it's inactivated. It keeps the shapes. It's going to keep its 3D shapes. And then you give that killed or inactivated cell or virus to the person, and that's what's in the vaccine. These don't just have one antigen, they would have all the antigens that particle has. So they are really, really good at making good, long-lasting immunity. But they are slightly more risky than the other categories because you are giving someone the whole entire pathogen. And you've got to be really sure that it's totally dead or it's totally inactivated. We don't use that many vaccines anymore that are like this. Not so much anymore. But when they don't cause the disease, they work great to make people immune. Okay, so now let's look at the next category down, which is live attenuated. That's this. Live attenuated. These are engineered. The virus has been engineered, or the bacterium has been engineered to lack some kind of infection component. They're lacking something that's really critical for them to actually infect people. We have eliminated or reduced the virulence, but they're technically still alive. This requires us to know really a lot about that bacteria, know everything about the virus, and know exactly what to do to make it live, but not be able to cause disease in the people. Those are called live attenuated. And so it's like it goes into your body and it multiplies, but it doesn't cause harm. And it teaches your immune system, oh, that's a foreign shape, I should make antibodies against it. Live
Which
attenuated.
one would you say is more risky? Because in both of them, the whole cell is being injected into it.
This one is actually more risky.
The top one?
Don't write that down, this is just my opinion. I mean, there are data about them, but this is more risky because if even one makes it past the killing, it's got everything it needs to infect.
But in that one, it's like a whole culture of stuff has been grown to have
Yeah.
specifically non.
Yeah. In this case, the whole culture is missing something really key.
So that's more 100% than the top one.
Neither one of them are 100%, but this is a little safer than trying to be extra sure that if you've got 5 million bacteria, that 5 million of them are dead. Because if 10 of them are alive, that's not good. That's not good enough. But both of these are not quite as safe as the next categories, which are subunit vaccines. So with a subunit vaccine, you're just taking only a piece or a few pieces of antigen. For example, purified spike protein, or you take certain enzymes or certain structural proteins from bacteria, not the whole thing.
Specific pieces of
Just
protein.
specific pieces, yeah. So specific pieces are not dangerous to us. But the drawback is they don't give as lasting immunity because we're only giving, like 1 to 3 pieces instead of 86, like if it was a whole cell. So if I go back to the stupid example of Grady in the hat, like this would be, you see this hat, that's Grady. The other is, you see Grady, that's what he's like. And I would have multiple things, multiple antigens to learn, oh, that's Grady. And any, specific piece of Grady, my body would have learned that. But with the subunit vaccine, it's definitely not dangerous, but it's also not as strong of a protection, in essence. A lot of times, we figure out what is the protein and we'll just genetically engineer proteins to make them. There's some vaccines that you give an altered version of a toxin called toxoid. Altered safe version of a toxin. That's a toxoid vaccine. Is there one more? Is this the last? of the vaccine types, or is there one more?
It's just this slide.
Okay,
It
good.
just says it overall.
This one I used to sometimes skip over for sake of time, but this I'm not skipping over this because this is what the current leaders of coronavirus vaccine candidates are using, which are DNA or RNA vaccines. And in these kind of vaccines, what you're actually giving the person is a piece of the DNA or the RNA, if it's RNA virus, into the person. So we're not injecting the people with antigens, we're injecting them with genes.
Is that kind of the same thing as a subunit though?
It's like an alternate path to a subunit. So in this case, you give the person the gene. Whoops. You give the person the gene, and the human cells make the antigen, and then build immunity to it.
Are you going to need to list these 5 steps?
No, because it's too much info. Let me do a truncated version of this. So with these, we're giving people a pathogen gene. Oops. And then our own human cells make the antigen to then fight it. That's what the current SARS-CoV-2 vaccines are, and that's why they have to be kept so cold. Because what they are is that they are DNA or RNA. It's actually RNA, I think. I think it's DNA. DNA of SARS-CoV-2 virus that we're putting into people, and it's got to last long enough in us for us to make a spike protein, and then we will mount an immune response to it. The advantage of this is it's much faster to make the vaccine. The disadvantage of this is that they haven't gone through the years and years of trials. Like until this year, this is kind of like, well, theoretically, this is the vaccine style of the future. The future's here. This is what the first corona vaccines are going to be like.
Well, the downside for this as a general is the downside in this year of the coronavirus vaccination
The
process.
downside is just that it's new, basically. It's a new method. And we've not followed people for 20 years afterward to see.
So if somebody got that vaccine and it was like into their genetic code, would they pass it on to their kids?
Oh, that's such a good question. This DNA doesn't integrate. That's so important. I'm so glad that you said that. This is not like giving people a lysogenic virus.
Okay.
The DNA doesn't integrate. So
But then how would your
important.
body make it then? If it's not.
It
the
will
cell?
last a little while, long enough for the cells to make it. And then when the DNA RNA breaks down, it's gone. So the trick with this is to figure out how much do you have to give a person for it to persist long enough for us to make some spike proteins that then we can form an immune response
So then why wouldn't DNA be breaking down if the COVID is specifically kind of made to affect like kind of us and stay in our bodies?
Oh,
Our bodies
because,
98 degrees.
DNA is not as stable as a protein. So if you think about how COVID acts,
So if it's outside the body or the cell, then it's way more.
that's, yeah, like even in a tube, purified, if it's at room temperature, it's not going to last. It's quite flimsy
Okay.
and short-lived. And that has to do with the structure of DNA, and it's got
Yeah.
3' hydroxyl that's easy to destroy in water. So yeah, these don't integrate and stay. They will, the piece will last as long as DNA or RNA lasts in the body, which is not long.
So do you know like long-lasting immunity, or is it just like,
We're not gonna know.
I don't know?
We're not gonna know. Because if you think about, when did we start this for SARS-CoV-2? It would be in March. Yeah. In the beginning, I thought, well, there's no way they can get a vaccine in less than 4 years. It's, that part hasn't been celebrated enough, actually, like, to be getting close to having vaccines after 8 months or whatever. What month is this? However long, 8 months? It's like insane.
Well, I watched.
So many people working so hard on it, yeah.
One video that I watched saying like how they can potentially speed up the process and use like AI machines that they can mathematically be like, we need this, this, and this, and like go through all like humans, you'll have to do all those tests over the years, where an AI can like kind of like.
Yeah, AI can help.
I'm really like, it'll like help, but then it'll still like,
Yeah,
it'll take away a lot of like the grunt work.
yeah, it can help. So I can't remember what I've told each class about, like the vaccine trial that Han and Sam are in, but they're in the Pfizer trial, which is this big drug company, Pfizer. They're worldwide. And the Pfizer trial is trying to get 44,000 people enrolled in the study. And half of them are going to get the placebo, which is a shot with basically like salt water and not much in it. And half of them are going to get the vaccine, which is this style. And the people who get the vaccine don't know which one, and the people who give it to them don't even know which one. There's somebody off-site that has the database with all the names. And so it's double blind. And they have to wait until 150 people in each of the groups catches coronavirus as a part of their normal life. And if they can get 150 people it has to be 150 people in the placebo group catch coronavirus. And then they will see how many people in the other group with the real vaccine catch coronavirus. And they're hoping that it's a big difference. And then they're also tracking every day and every week, like what's happening to the people and their symptoms. So Juan has an app on his phone, and he's supposed to go in every day or every week and say if there's anything wrong. So, but that Pfizer just announced that they're not gonna have enough data until December. So I guess people aren't catching COVID fast enough. I don't know.
You just go out now.
They just tell them to like go live your normal life. Because like you can't tell. Could you try to catch? Could you go try to catch it so that we can finish this study? But at least people are volunteering. He sent me the link to volunteer, but I just don't have time. I used to go to Kingsport every 3 weeks, and I can't. I've got class. But I'm proud that he is and Sam. There are other ways that you can get vaccines. Did you all ever have the flu mist when you were a kid?
No.
It didn't work as well, so they've kind of quit doing it. There's something about going straight into the blood is a little bit more effective than trying to get the vaccine across your nose epithelium. There used to be ones that you could put on a sugar cube and have people eat it. If you eat or ingest a vaccine, that's difficult because they have to survive digestive system. Survive the digestive system. And stay intact. So that ridiculous word at the end is intact. You have to stay intact. So you eat the vaccine, and it goes into your stomach and passes through stomach acid and all of those digestive enzymes that you've got, it's really not going to make it. Our digestive system will destroy the shape. So
What last one said?
intact, yeah. Can't you tell? Everybody in our family has bad writing except for Han. This is very nice. I think they're forced, like you can't not have good writing in AD schools because you'll get an F. Too strict. Much too strict. When I was your age, like, there was still a lot of hope that we could grow bananas with vaccine in it and send it to poor countries and all the kids could get their vaccine that way. It's just not working out. After 20 years of trying. So as nurses, when you become nurses or other health professionals, it's really, really important to try to convince people that it's worth their time to get vaccines. And we don't now live in a world where we have the really deadly diseases that kill people anymore because we made vaccines for them. SARS-CoV-2 is going to change that. But it's also borderline like, well, that's not that deadly of a disease. Most people survive it, which is true. And children are not harmed from it. So these two diseases, this one is the one that causes whooping cough, or whooping cough if you live around here. Polio is one that causes paralysis. And both of these are fairly deadly, especially in kids. So you can see here, it's got what year did it happen? And then it shows when was the vaccine introduced. So in the 20s, there were a lot of whooping cough and a lot of kids died from it. Like everybody would know a kid that had died from whooping cough, or a baby usually. And then after the vaccine was introduced, when people started getting vaccinated, we don't really have diphtheria deaths so much anymore. And now hardly anybody knows a baby that died from whooping cough because that's one of our normal vaccines. That's in your DPT. The D is diphtheria. Same for polio. Doesn't go back far enough, but polio was really deadly for so long and caused people to not be able to walk. So some people survive it, but they can't walk. And then there was a vaccine.
Nervous system?
Yeah, it attacks your nerves from the feet up. And so you get paralyzed from, and Franklin Delano Roosevelt had it, but he was able to hide it from people because the news media cooperated with him. Can you imagine? Like, that's crazy now. It's like, can you not let people know that I'm paralyzed? Because TV was just barely, okay, we'll work with you on that. And so he was never really photographed, or very, very rarely photographed in his wheelchair and stuff, but he was from polio. Is that his class over?
Practice is about to start.
Oh, practice is about to start. Well, it's useful for that too. I'll start back with the same slide set for Friday, but also bring the new one about immune disorders. Oh my gosh, I meant to take off some of these political people. It's kind of outdated. Oh well.